This video is designed to help you review some of the organic molecules basics that we've already covered in class so far. And so what we're going to start off with is just kind of reviewing briefly how to decipher or draw kind of a calculate or skeleton structure, which is where the carbons and hydrogens in the organic molecules are replaced by lines and points. So let's say, for example, that we have a molecule that is 3 carbons long, and of course each carbon will complete the octet by adding hydrogen. All right. So if we had to write in a molecular formula for this particular compound, we would call it C3, and there are a total of 8 hydrogens. And this, as we'll come to learn later, is called propane. So now let's pretend that we want to draw a skeleton structure for this molecule. For every point or bend in the molecule, we're going to assume that that's a carbon. So if there are 3 carbons, we'll count 1, 2, 3. And you'll kind of draw your lines in a zigzag structure to kind of help visualize or remind yourself that each of those carbons, in this case, is going to be tetrahedral when they're just carbons and hydrogens connected in a chain. So again, each of these points is representing your carbons. And then what we would assume is that there are enough hydrogens to complete the octet. So this carbon right here would already have 1 bond, which means we would assume it needs 3 more bonds of hydrogen. The carbon in the center already has 2 bonds, so we would assume that it needs 2 more bonds to hydrogen. And then finally, the bond on the right also has just 1 bond, so we would assume that it needs 3 more bonds to hydrogen. And so for a complete octet, carbon has 4 bonds. So if it's only bonded once, it'll need 3 hydrogens. If it's bonded twice, it'll need 2 hydrogens. If it's bonded 3 times, then it will just need 1 hydrogen. All right. So let's do an example with a double bond kind of right quick. So let's do this one. And we'll put in an oxygen maybe, and maybe a nitrogen over on this side. Okay, so what we're going to do on this one is we're going to try to decide how many carbons and hydrogens are in the structure. All right, and so I'll try to go through and highlight every place we'd find one. So at the end of each line is a carbon. And then also be careful, anytime you have a double or a triple bond, there will be a carbon kind of at each end. And then we'll have a carbon on this end near the oxygen. All right, so it looks like overall we have a total of 1, 2, 3, 4, 5 different carbons. Now let's go through and kind of count the hydrogens. So this carbon here has just 1 bond, so he would be paired with 3 hydrogens. Same thing for this carbon, needs 3 more hydrogens. Now if we look at this carbon attached to the double bond, he already has 1, 2, 3 bonds, so he'll just need 1 hydrogen. Same for the carbon on the other side. And then finally, this carbon attached to oxygen just has 1 bond, so he'll need 3 hydrogens as well. So it looks like we're going to need a total of 11 hydrogens. That's 6 on the left, plus 3 on the right, that gets you to 9, plus 2 is 11. All right, then finally, if we were completing the formula, we have 1 nitrogen and 1 oxygen as well. Okay. Now what we're going to do as kind of another part of review is we're going to practice filling in lone pairs on atoms. And so again, this is most commonly needed on elements like nitrogen, oxygen, sulfur, where we may just show the bonds but may have left out the lone pairs. So typically, we have oxygen kind of here on the right, and it's in that typical kind of 2-bond structure. But from those 2 bonds, it only has 4 electrons total, 2 electrons coming from each of those bonds. So in order for it to have an octet, we need to add in 2 more lone pairs. All right, and that will give it a total of 8 electrons. So lone pairs are added to complete the octet. Now if we look at nitrogen, it has 3 bonds for a total of 6 electrons. It is 2 electrons short of having 8 electrons, so it needs 1 lone pair to complete the octet. All right, so now with lone pairs, that brings us to our next section of the review, where we're going to take a little bit of time to review geometries or shapes. So again, even though we're drawing in 2D, these molecules really have 3D shapes. So let's take a look at kind of this portion of the molecule with the N attached to kind of 3 parts there. So if you remember, we kind of made a distinction between electronic and molecular geometry. The molecular geometry is when we take into account how the lone pair affects or pushes down kind of the bonds of the molecule to change the overall shape. So here we have kind of 3 bonds being pushed down by 1 lone pair. So if we were to redraw this kind of portion of the molecule, it would kind of look more like that. And so when you have 3 bonds being pushed down by a lone pair, that's called trigonal pyramid. If we didn't have a lone pair and the bonds were all in the same plane and spread out evenly, that would be called trigonal planar. All right, so now let's go to the next part of the molecule with the double bond. And so just for ease, I'm going to draw in kind of another carbon there. So here we have no lone pairs on our carbon, and there are 2 bonding regions on each side. So as a result, that will make each of these carbons linear. Okay. Now, let's take a look here and see if, oops, and I think I'm realizing I meant to make this a triple bond earlier. Sorry, and didn't draw that in. So I'll take that back. There you go. Hope you watching the video this far along. That way you can remember that. All right. So anyways, still linear, 2 electron regions, no lone pairs. All right, then now let's take a look at this last part of the molecule with oxygen over here. So if we kind of focus in on the oxygen, we see that it has 2 sets of lone pairs that are pushing down 2 bonds. And that is what we'll refer to as bent. So again, we just want to kind of refresh on those terms and get in the habit of thinking of molecules in 3D and trying to kind of somewhat represent that as we draw them, on our papers. All right, so now kind of in the spirit of geometries, let's review hybridization right quick, which is really kind of investigating how do the electron orbitals overlap to actually give us these different bonds. So if you remember, we had a few different types of hybridization, sp, sp2, and sp3. And what this does is shows us how the atoms s and p orbitals are mixed. Okay, draw those in there. So for sp hybridization, you're taking 1 s orbital and 1 p orbital and mixing them. For sp2, you're taking 1 s orbital and 2 p orbitals, mixing those all together. And then for sp3, you're taking the s orbital and all 3 p orbitals and mixing them together to generate new hybrid orbitals that look like partly s and partly p. Okay, so now right quick, let's kind of go back and review how to determine whether an atom is sp, sp2, or sp3 hybridized. So since sp hybridization only mixes 2 orbitals, there should just be 2 electron regions around that atom if it's sp hybridized. sp2 mixes 3 orbitals, so that would correspond with 3 electron regions. sp3 mixes 4 orbitals, so that will correspond with 4 electron regions. So I'm going to redraw our same molecule right quick up here. So we had N on the end. And then the triple bond. Let me not make the same mistake this time. And then we had an oxygen here. And I'll go ahead and fill in our lone pairs. All right, so let's go through and kind of assign a hybridization to each atom. And we'll start with our carbons on the end here. So we know, even though they're not shown, that those carbons have 3 additional bonds to hydrogen. So if you include that bond to nitrogen, they would end up with a total of 4 electron regions. So that means each of these carbons would be sp3 hybridized. And typically, if a carbon is just attached to a single bond, that's the case. So you can kind of start to observe that pattern. All right, now let's take a look at our nitrogen. If we look around it, it has 3 bonds and 1 lone pair for a total of 4 electron regions. So again, its hybridization as well will be sp3. All right, now let's see if we can focus our attention on this carbon, or these carbons rather, that are attached to the triple bond. So on either side, they just have 2 regions of electron density. They have the single bond and then the triple bond area. So if there are 2 electron regions, then you'll have those carbons be sp hybridized. And then finally, let's take a look at our oxygen. Our oxygen, if you count the lone pairs, as you should, has 4 regions of electron density. So it'll be sp3 hybridized. All right, so now right quick, let's remind ourselves of the sigma and pi bonds right quick, and that'll be our last portion of the review. I'll give myself a little more room here. All right, so first of all, just kind of being able to label, which bonds in an atom are sigma bonds and which are pi bonds. So the sigma bonds, kind of represented with a little Greek letter sigma, are formed when you take the brand new hybrid orbitals and overlap them, okay? And so this is typically what we refer to as our, just single bond, right? The pi bond, on the other hand, is when you take kind of the unhybridized p orbitals and have them interact. Now, if we remember, kind of the breakup of sigma and pi bonds varies based on whether you're working with a single bond, a double bond, or a triple bond. So for a single bond, it consists of just a pi bond. All right, I'm going to draw that in there. So you're using your new hybrid orbitals to make that bond. A double bond consists of a sigma and a pi bond. So you'll have your sigma bond kind of running through the middle there. And then your pi bonding kind of going over the top and bottom. And then finally, you guessed it, for a triple bond, it has a sigma and 2 pi bond components. So we'll have our sigma bond in the middle with those hybrid orbitals. We have 1 set of p orbitals kind of going up and down. And then the other set of p orbitals, if you can kind of imagine, are coming in and out of the plane. So think of them sticking kind of in and out of the paper here. All right. So now let's suppose we asked a question here about our molecule, and we asked how many sigma bonds are within the molecule. So what we would do is we'd kind of go through and count. We know that every single bond is a sigma bond. And then don't forget about those extra hydrogens bonded onto your carbons. I'll kind of write those in here. Okay, and then also that triple bond will have one of its parts be a sigma bond. So total, we have, change my highlighter color here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 sigma bonds. Then we have 2 pi bonds that help to make up that triple bond. Okay. And again, those pi bonds are formed from the overlap of non- or unhybridized p orbitals. Okay. All right. Now let's see. I think that's all I want to review with you guys today, because I think that'll take care of most of the info that you'll need to kind of do the review practice problems. All right, so thanks so much for listening and hope you all have a great rest of your day.